Welcome to the Data Future channel. This is Shekhar and I am a data scientist. So in this particular session, we are going to develop a machine learning model which can predict the quality of the water, whether that water is potable. So potable means the water is safe for the human consumption or not. So there are different the values which are considered uh, and on which it can be concluded that whether the water is safe for drinking or not. So out of that, we have to check the hardness of the water, we have to check the pH value, we have to check the solid present in the water, the sulfate, chlorine level. So these values we have to check, and later on we can come to the conclusion that whether that water is safe for the consumption or not. So this is the concept behind the building this particular project. So here we are building a end-to-end project which is based on the classification model. Okay, so already we know that what is the water potability. Potability means whether that water is safe for consumption, human consumption basically. Okay, so we'll check the other parameters also. So let's get started. So initially the first step is we have to import the required libraries or the modules. So here the NumPy, Pandas, Matplotlib, Seaborn we are importing, and these are we have to use for data manipulation and data visualization also. So we can carry out the exploratory data analysis also. Now, second step is we have to load the data. Now, our data is in this particular file. So I'm sharing this file with you. Check the description. And parallelly, you can see this video and try to build the model, right? So yes, I'm using a pd.read underscore CSV. Now you can see that uh, these are the columns which are present in the data set where you will see the pH, hardness, solids, chloramines, sulfate, conductivity, organic carbon, trihalomethanes, turbidity, um, uh, turbidity, and the last one is the potability. So potability is the target variable where this water is safer for the consumption or not. So 0 means water is not safe for the consumption, and 1 means it is safe, right? So we will list down the columns here. So you will see these are the columns are there. Now you can see that the pH value. Hardness is the capacity of water precipitate soap in mg per liter. The total TDS is there. TDS, total dissolved solids in ppm. The chloramines, amount of chlorines in ppm. Sulfate, then conductivity, whether the water is electrical um, it can conduct the electricity in terms of these values, right? The organic carbon, then trihalomethanes, turbidity, the measure of light emitting property of the water. Okay, and its unit is nephelometric turbidity unit, right? Then last one, the potability index, water is safe or not, right? So 0 means unsafe and 1 means it's a safe. So come to the basic data analysis. So this data set contains 3276 rows and 10 columns. We can check the data type of each column by using a D types. So this is the data. So everything is a numeric variables are there. Then we can check the information about the data. Now you can see that our total value is 3276, but some values are missing here. You can see that are not matching means these are the missing values, right? So we will see, we can check the statistics by using this one. So where you will see the count, mean, standard deviation, minimum value, 25th percentile, 50th percentile, 75th, and maximum value in that particular column. So from this you will get the basic idea about the statistics of each column, and here everything is the numeric one, right? So after that we can check the whether there is a duplicate present in the data set. So by using a dot duplicated dot any, so it is showing false, means there is a no duplicates. After duplicates, checking the duplicates, we have to check the null values, and we are using is null dot sum is there. So now you can see there are so many null values are present in the three columns. One is pH, then sulfate, and trihalomethanes. Now these values we have to check, but how much percentage of the null values are missing, that we have to check. So we have to divide 491 divided by 32, how much is that, 3276, so you'll get the percentage. So same thing I'm doing here. I'm creating this the data frame here in the null df, then changing the columns and null count, and adding one more percentage column where I'm dividing it by the length of the data frame. Okay, and I'm rounding it up to the two decimal points into 100. So here you will get the percentage missing values. Here you will see 15%, then here 24%, and here is the 5% missing values. Now, next thing is we have to input these missing values, right? So before that, we can check these missing values by using a heat map, by using a visualization library, Seaborn. Okay, so you will see, yes, the three columns having the missing values, right? So this yellow marks you will see as the missing one, right? Now how to handle the missing values? Now we have to check the distribution of this one. So the distribution of these columns we have to check first. So I'm using a water DF, a water data and pH plotting the histogram. Then same for sulfate and same from the trimethanes. And I'll check whether they are normally distributed or the data is skewed one. So from this particular case, what we can see, the data is similar to normally distributed, not approximately. So our strategy is we can replace these missing values with mean value. Okay, that is the best way, right? So you can check the KDA plot also uh, here, right? For trihalomethanes, I plotted the KDA plot. Okay. Now, next one is the missing value imputation. So what I'm doing here, you can see here, this is our pH column, and in this pH column, we are filling dot fill NA the values with the mean value of that. So you can calculate the mean value of this particular column dot mean and fill it in this particular. So finally you will get the column which is without null values, means all the null values will be filled with the mean value of this column. The same strategy you have to apply for these two columns again. You just have to run this and check whether there is a null values are there or not. Yes, you can see there is a no null values in the data set. Now moving forward, we have to check the correlation among these numeric values, because you can see that everything is the numeric one. So you will see this is the correlation you will see, the Pearson correlation coefficient you will get. And from this, you are not getting any idea, but you can plot the heat map also so that you will get the idea. So I'm putting here the SNS.heatmap and the correlation matrix, which I have created here by using a function .core. Okay, and anode true and CMAP is the Coulomb. And when I run this, you will see, yes. So I think there is a no any a significant correlation among these variables. So yes, so we can keep the all the features in the data set. Okay, this is all about the correlation. Now you can check by the upper try matrix also by using this because this is the safest one you will see, and this is nothing but the correlation matrix itself, but in the another form you will see this correlation you will get from this visualization also, right? Okay, so you can use that one or this one. It's up to you. So for that you need to use this np dot uh, treu and correlation matrix which we are using here, right? So that we have to use. Okay, fine. Then I want to plot, visualize the data so that I can check the distribution of all the columns, right? All the columns. Now, what I'm doing, I'm using data hist plot is water data dot hist, and here I'm providing the figure size and the color is this, right? So when you run this, you will see. mm Yes, the histogram of each and every column. So this is pH, hardness, solids, okay, conductivity. So yes, almost every column is nearly equal to normally distributed. There is a no here you can see there is a some right skewed data is there. Here is the left skewed data is there. Okay, that data you can see it by using a box plot also. We are going to plot the box plot also. Okay, so what I'm going to plot, so I want to check what is the difference between the two histograms. Um, uh, 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 the histogram of each column with respect to potability means target value, target variable. So that from that you will get the idea. Okay, so for that I am running a for loop and SNS hist plot. Here the way I'm providing the data, and every time it will consider the column from this. And KD is true, that is very important. And hue we have to consider, that is the potability. So here in the legend you can see the potability 0 and 1. So from this case you will see this the blue is the water is unsafe, and this uh, the orange is water is safe. So for these two values we can plot, and always this graph is always lesser than these unsafe values, right? Everywhere. So you can easily distinguish this the data set, right? Yes, we can see this, and here there is a lot of difference between the safe and unsafe water, right? This is safe one, which are having a less number of counts than unsafe, right? So what we can see from this, what I'll do, I'll check the what is the difference between the minimum value with respect to potability, and for that I'm grouped by the data set with respect to potability mean, and considering the mean value here. Now you can see that with respect to potability, you can see the mean values, and here the pH value is slightly less. Here is the this is slightly less. This is slightly less. This is something greater. This is less one. This is less. Okay, but from here you are not getting any idea because we are considering mean values here, and these mean values are almost same. There is no any significant difference. So it is difficult from here to check the significant the features, right? Yes, so we can plot here the box plot also by using sns.boxplot, and here I'm using this water data and the column. So each time it will plot the box plot by using a Seaborn. So now this is for pH value. Then this is, and you can see that beyond the both the viscous, there is a lot of outliers everywhere. You can see. Okay, and this is all about the box plot. Then We are checking the count plot of this uh, um, sns.count plot, and why it is taking too much time. Uh, let's Okay, something is wrong with this. So simply what we'll do, so I'll do one thing. I will take this and check the value count of the for this. Okay, dot value counts, value counts, and you can check portability. Oh, okay, why it is taking a too much time? Don't know exactly. Let me just clear this and run this. Okay, now you can see that there is a 0 and 1. These values are there. So 0 means unsafe water records and safe water records are there. Now you can plot the bar plot for this. I'm trying to plot it by the this SNS also. This is Seaborn, but this is not happened actually. We'll check later on, right? So here you can see the 0 values are greater than 1, means unsafe value and safe value. Okay. The next step is the data preparation. So here we have to prepare the data like we have to split the data into target and independent variable. This is our target variable and X is independent variable. So what I'm doing, I'm dropping the portability column from that data set and creating the X, and Y is our dependent variable, that is target variable. So X head and Y head you can check. You will see there is a no portability column here. Now next one is the feature scaling. So these features are having a different scales. So we have to scale it to a common. We have to bring these all the columns on this common scale, and for that we are having a feature scaling one. So from sklearn dot preprocessing imports standard scaler, and we have to create the object of it, and then we have to apply this object by using a fit underscore transform to this x. X means this data set, and you will get the all the data is transformed. So this data is transformed with zero mean value and one standard deviation. So that is called as a standardization actually. Next one is the we have to split the data into training and testing, and as usual we have to select the 10 test split model from the model selection from sklearn, and we have to create this one. So 10 test split x. Now here is x scaled we have to take. We can't take x values. We have to take the x scaled and y. Okay, and then you will see then 20% data is for testing, 80% is for training. Okay, now you run this. Yeah. Now X-train and Y-test, X-test safe, you can see this much data is training and this much data is for testing. The next important part is the model building. Now here I am going to build a 9 classification models. So one by one I'll see. It's the first one is the logistic regression, second one is the decision tree, third one is the random forest, fourth one is the extra tree classifier, fifth one is the support vector classifier, the k-nearest classifier, gradient boosting classifier, naive Bayes and Ada-Bayes classifier. These models I'm going to build. Okay, now for that you just have to import these models from the sklearn. Now logistic regression from the linear model, decision tree from trees, random forest from ensemble tree, extra tree is from ensemble, and gradient boosting is also from the ensemble. Ada-boost is also from the ensemble technique. So SVC is from SVM. K neighbors classifier is from neighbors, and we have to use the Gaussian naive Bayes actually. Gaussian naive Bayes we have to use here, and from the naive Bayes. Okay, so we have to run this so that you can import all the algorithms. Now you have to create the object of each and every model here. Okay, but instead of creating the object, what I'll do, creating a pipeline actually. So with this pipeline, we are going to do first thing we are doing, it's a model training. Second one is instead of using this one, so you can go and watch my previous videos also where I have separately built these models. But this is not the good practice actually. So whenever you have to build the multiple models, then you have to create a pipeline, and in one shot or in one go you have to create the final accuracy score of these models. So you can watch my previous videos. So creating a one by one model and predicting it and then checking the evaluating model will take a lot of time. So without doing these things, we are going to develop a pipeline, and for that we need to just import the cross-val scores, because cross-validation we are doing it in this case, right? Now, yes, first we have to build this model. Yes, we have created this object of each model. Now I have created the list of models here. I am listing here, and then features is xscaled, then label is y, CV is 5, means 5 folds it will create, and accuracy list and model name. So what I'm doing here, so I'm running a for loop model in the models. So it will take the first model, then it will create a name. It's a name of the model, that is the logistic regression. Then I'm giving the cross-val score function with model, that model, then feature, then labels, and the scoring is accuracy, and cross validation, uh, the fold is 5, means 5, it will divide the data into 5 folds, and according to you will get the 5 accuracies. Okay, and finally I'm for that particular model I am taking the mean of this accuracy, because this will give the 5 list of 5 accuracies, one accuracy for one float, like 5 accuracies, and I will take a mean of these 5, multiply with the 100, so it will be in percentage, and going to append this accuracy in the accuracy list. Okay, and the model name, appending the model name in the model name list, right? So once it is, it will run for this nine iterations, calculate the accuracy and put it here. Now here what I am doing, I'm creating the data frame of two lists, where the model is the model name and cross-val accuracy is the accuracy. Okay, so when you run this, it will take certain time, because it will uh, run for 9 models, and for 9 into 5 means 45 times it will generate the accuracy. So for each model it will generate the 5 accuracies, because it's the 5 folds. If you can give the 3, then it will create the 3 accuracies and will take a mean of it. So it will take certain time, because it has to run through the 45 iterations. Good. So from here, we are getting a good accuracies, and you can see here the SVC is giving us the good accuracy actually. Okay, fine. So SVC will give you the good accuracy. Uh, so we can evaluate that also. So for the SVM, here we have created SVM, then extra T is 63%, and then after that there is a random forest is third one. So for 3 models, we are going to um, build a classification report. So we have to check these values also, like accuracy, precision, recall, these values also we have to check. Okay. The first one is for random forest. So random forest, you can check the precision, recall, F1 score, okay, and accuracy is 66%. Okay, fine. This is for SVM. So I'm using a Y predictions. I'm taking the predictions here, and here 69, uh, 27, 39, and accuracy is 0.67. And last one is this one. Okay, so we are getting here the less F1 score we are getting uh, for SVM. Uh, the F1 score is quite good for random forest, and mm, this this score is also good. But from here, what I can observe is there is no there is a less difference between the 0 and 1 class. So what I'll do, so I'll consider here the random forest, because the random forest is very the popular model which we can build, develop, and which is very we can it has the very high explainability. Okay, we can explain it in easy way, right? So we are considering the random forest here. So for you can plot the ROC curve here. So you can do it for ETC, that is the extra T classifier. So where there's value is 64 percentage area, and for this score here you can see it's a 0.65. So the random forest is good for this particular. So what I have, I'm selecting a random forest and for the hyperparameter tuning. Okay, so for that hyperparameter tuning, you have to just import the grid search CV and stratified k-fold these algorithms from the model selection. Okay, and we have to create the parameters. So parameters like minimum sample speed, minimum sample leaf, n estimators, and criterion Gini or entropy, and then you have to use the three folds, and you have to use the grid search CV, where we are providing here the model, random forest classifier, estimator, and scoring is accuracy, and we are fitting it to the X train and Y train, and we are calculating the best parameters. Okay, and after the best parameter we are considering the best estimator and checking the final results using this. So this is all about the hyperparameter tuning, where I am doing everything. So you can go up to my previous one where we have done lot of grid search CV, implemented grid search CV algorithms to find the best hyperparameter, right? So I will run this because it will take certain time, right? So meanwhile, we'll check. You can go and watch the grid search CV and the randomized search CV algorithms, how we have used there to find out the best parameters, right? So after finding the best parameters, you have to check the best estimator, and you have to select that best estimator. Means best estimator means the best model, best random forest model, and you just have to fit it, and then again you have to predict, and finally you have to check the classification report whether there is a improvement in the accuracy or not. So that is the basic objective here. All right, so we have to wait for a few minutes, and then we can go ahead with the final accuracy of the random forest model. So what happens in the grid search CV? Grid search CV, it will consider each and every parameter in this in this grid and go and calculate the accuracy. Uh, okay, so so what will happen and try to find out the best parameters which are giving the best accuracy. So just like it will try to search each and every aspects of this parameter and gives you the best parameters. Okay, but randomized search CV where it randomly selects the parameters from this particular list. Okay, so whenever there are more number of parameters and there are a lot, our data set is very big. In that case, you have to go for the randomized search CV. But if the data set is less and the parameters are less, then you can use the grid search CV basically. Okay, yes, we have to wait. Okay, and here once we get the best estimator, so I'm using this grid search CV RF, this the object we have created. Uh, dot best estimator means it will give you the best model with all the this best hyperparameters, right? And then again you have to train this model, and then you just have to do the predict for X-ray. So it will give the Y prediction for best, and finally you will get the you have to print the classification report for this Y test and Y prediction base. Yes, we got this. Now, yes, you can see the entropy is the best criterion it has selected. Then second one is the minimum sample leaf is 1. Then minimum estimators are 100 and minimum sample split is 2. It has created. And this will give the best result. So now I will select the best. Okay, I'll show you what exactly is here. Best estimator. Yes, you can see that random forest with the best estimator. So it will consider these parameters, right? Now next one is you have to fit and print Y predict, and you have to print the classification report for this particular model. Yes. Now there is a slight increase in the accuracy, 67% is there. So earlier it was for random forest, it's a 66%. You can see. Now the accuracy is increased by 1%. This is a good improvement here. And finally, we are printing this accuracy 66.77%, right? For the random forest. Now we have to build a predictive system for check the water quality. Now here I will take the user input from user and create a data, and this data I'll transform, and the best estimator will predict whether the water is safe or unsafe. When safe is there means it is 1, unsafe is 0. Okay. So try to just do the columns. You know that you have to import. So what I'm taking, I'm considering some examples from the data set. Okay, I'll consider this example. From this example, I'll put the values, right? So you just run this. Yes. The first value is 8. So I'll take 8.1. That is, then hardness value I'll put as 224.5. Then solid value is 19,000 I'll take. I, I have taken the values for the reference purpose only. Then I'll take 9.5 here. 9.5 is the chloramines. Then next one is, okay, sulfate value. Sulfate value is 333. 335 I'll take. Then the conductivity value you have to consider is 418, so I'll consider 420. Then which one is organic carbon value is will take a 17. Okay, the trihalomethanes is 66, so 66.5, and turbidity uh, value we have to consider is 3.5. Okay, 3.5. I think this is done. Now the data is there. Now data is stored in this all the variables. Now these variables, I will create a list of these variables. Okay, now input data is in, but we have already applied the standard scaler, right, for the scaling this, transforming this. So I'm applying here the standard scaler dot transform. So it will transform this all these values, and you will get the the data is ready for the input to the model. Now this data I'm using here for the best model. So best estimator I have considered from here. This is my best estimator, and I'm predicting the water data, and what model will predict is 0. So means this water is not safe for the drinking one. So I'll convert into a understandable way. So if the prediction I'm considering the 0, I'm accessing this array. So 0, water is not safe, and if it is 1, then water is safe for the consumption. So it will print water is not safe for consumption. So what I'm writing here, I'm creating a writing a function here. In this function, I'm directly taking the input data and directly printing the output. So you have to run this function. So I am simplifying here, and here you will see one by one you have to input the values. Now for inputting the value, I'll select these values actually. Then 7.65. Okay, second one is 240. Then third one is 14, 245. Okay, then 6.28. Okay, then 373 here, 373. Okay, 373. Okay, then 416, 416 is there. Then 10.46, and then 85.85, 85.85, and turbidity is 2.46, 2.43. Okay, when I enter this, the water is safe for the consumption. So directly you will get the output from this, because I have used the input data and directly I am using the function here. So I have written the function here, and this function is directly transform the data first and then use the best estimator to predict. And here I'm using these predictions. So like this. Okay, so this is all about the end-to-end project where we can build the machine learning model which can predict the water quality, whether it is safe or unsafe for the drinking purpose, right? So you can save this model, and you can load this model also. So this is the next part, where how to save the model and how to use that model for the further prediction. This is the part of deployment. So coming videos, I'm going to explain this also, how to deploy the models, machine learning models, and use it for the further the predictions. Okay, for the new data. So this is all about from my side. If you have any questions, you can ask in the comment section. I'm providing the data set. You just go through this data set and try to build your own model. Try to do the play with the data, do the exploratory data analysis. Just go through what is uh, the maths behind this, all the algorithms, so that you can understand the each and every concept thoroughly, right? Thank you. Thanks a lot.